Okay, so let's begin this class officially. Good afternoon, everyone. Welcome to APNIC e-learning web class. This is IPv6 addressing and subnetting. That's a topic that we are going to cover for this afternoon. Now, every Wednesday, APNIC training team conducts IPv6 related sessions. So 4 1-hour sessions, and this is the last one. We've covered a lot of things throughout the day, from IPv6 overview, IPv6 address planning, and also IPv4 to IPv6 transition. So if those things are also interesting to you but you've missed it, please feel free to check our YouTube channel. We have a recording uploaded there. Okay, so today, just some minor housekeeping things before we start. Today is the 5th of March in 2014. It's 4:30 in the afternoon from Brisbane in Australia, where I am broadcasting this class. So wherever you are in the region, hopefully you are having a great day, and I hope you will enjoy this class. I also want to introduce myself because we will be together for the next 1 hour or so. My name is Cheryl Hermoso. I work as a training officer for APNIC. And my specialties, as you can see there, are on DNS, DNSSEC, Systems, Network Services, Network Security, IPv6, Internet Resource Management, and also Routing and BGP. So these things we do cover as part of the team. We do face-to-face workshops to the different areas in the Asia-Pacific region to conduct trainings, tutorials, and also 3-day or 5-day type of workshops. Okay, Anil said that the audio is breaking. We'll try to do something about that if the issue is coming from our side. So also, would you be able to check if the issue might be your internet connectivity? That can also be an issue, or the host where feed is coming from, which is with Adobe Connect. Anyway, so yeah, we've done a few things. Hopefully that has improved it. If not, please let me know using the chat. But what I'm going to do is just continue on with the class. See if you can still understand what I'm saying. I'll also try not to speak too fast. I have the tendency to do that. So I'll try to speak a little slower just so you can pick up the words that I am saying. Okay, so let me know if there are still issues, right? Okay, so I was about to say, I was introducing myself, and that's what we do in the training team. So this session will last for 1 hour. Hopefully by the end, and you've stuck with us, we will send you a link to the survey, so a feedback form. So if you can fill that in for me, that will be great. Okay, so this is what we are going to cover for the next 1 hour. We will have, our focus mainly is on the architecture of IPv6, IPv6 text representation, how to write down IPv6, what are the different types of IPv6 addresses, and what do we use them for. So it's kind of confusing when you look at an IPv6 address and you don't understand what is it for, or what is the coverage, meaning if I have a link local address, is it visible from the global internet? If I have a global address, what can I do with it? What are the different parts of the IPv6 when it comes to its architecture? What are the different parts of its address? We have an interface ID, okay, we have the network bits, and how do we obtain an IPv6 address? So we will look at IPv6 auto configuration, which is a way to automatically get an IPv6 address into an interface. So as soon as you have enabled IPv6, you should have an IPv6 address as well. So we will look at that, and I think that will be just enough for 1 hour. We won't have enough time to cover everything about subnetting, but I will give one, or I think just one example, and then I have, towards the end, I have about 3 example exercises that you can do on your own pace. If you have done it and you think you're not sure whether it's correct or not, then you can come back to me and ask me, verify whether your answer is correct. Right? So that's our plan for this afternoon. Okay, let's begin with IPv6 addressing. So just as a recap, what is IPv6? IPv6 is a newer version of the Internet Layer Protocol that is functioning in the TCP/IP protocol suite. So the idea behind it is to have a replacement IP protocol, okay, that would eventually replace perhaps, or maybe as of the time being, maybe just to complement the currently existing IP version 4. So IPv6 is a newer protocol. The goal is to have the computers, the machines on the internet running IPv6 because we are running out of IPv4 addresses, and soon enough there won't be enough IPv4 addresses to use for all the devices that connects to the internet. So that's why we have IPv6. We're running out of v4. We need to sustain the internet. Okay, so how do we write an IPv6 address? This is an example of an IPv6 address, as you can see down here. Okay, in IPv4, how do you write an IPv4 address? It's using what we call as a dotted decimal format. Okay, so you have a 32-bit digit, you subdivide it into octets, okay, groups of 8, and then represent that as a decimal number separated by dots. That's why we call it a dotted decimal format. Now in IPv6, okay, the size of an IPv6 address is 4 times as large as an IPv4 address. So an IPv6 address consists of 128 bits. That is 4 times bigger than an IPv4 address. However, when we talk about the entire IPv6 address pool, which means all the addressable devices that can be used, okay, that can be addressed with an the entire IPv6 address pool, that is a lot bigger than IPv4. IPv4 can only address a maximum of 4.3, roughly 4.3 billion devices. IPv6, because this is exponential, can do 2 raised to 128, which is around 3.4 times 10 to the 28, I think, something close to that, or it's 3.4 billion addresses. So that is a lot. So that may be enough, okay, to sustain the internet just a little bit longer. Now, IPv6, as I've said, consists of 128 bits, but when we write it down, we are using hexadecimal digits. So values from 0 all the way to F. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. So one hexadecimal digit represents 4 binary digits, or we also call it as a nibble. Okay, 4 bits is a nibble, is a hexadecimal digit. So when you write it down in hex, then we're not using 128 bits anymore. We have somehow shrunk it down. We are now using 32 hexadecimal digits, right? So this is actually an example of an IPv6 address, but as you can see, it is not 32 hex digits. Okay, how many can you see there? That's 4, 8, 11. You have only 11, but that is a valid IPv6 address. We will see in the next slide why it is so. But what I wanted to concentrate at this moment is this. This is a field in an IPv6 address. Okay, this is in hexadecimal digits. When you write it down in binary, it should be A is equivalent to 1010. I assume that you know how to do this. Okay, 9 is 1001. 1 is of course 0001 in binary, and 0 hex is 4 zeros in binary. Okay, so these are what we call as nibbles. Every 4 digit is considered as a nibble. Okay, so when you look at it, you've seen an example here, but when you look at it, the hexadecimal values consists of 8 16-bit fields. So that's how we subdivide our 32 hexadecimal digits. We subdivide them into 4 hexadecimal values each, which means 16 bits. Okay, I hope that you can follow. And that is, each of the field is separated by a colon. Okay, we are no longer using dots, we are using colons. So each X value here represents 16 bits or 4 hexadecimal numbers. So if you want an example, this is an example of a complete IPv6 address. Okay, FE38 all the way to 683D. It's very hard to memorize this. If you have a complete IPv6 address, that is a lot of hexadecimal values, and it's very hard to remember them. Okay, but there are ways in which we can shrink or shorten an IPv6 address. Well, if you have this example, of course, there's no way to do that. But as you can see, when you get your IPv6 address later on, okay, you will see that most likely you will be using the first few values, which has a lot of zeros. Okay, so welcome Altan, Gerald. Hopefully you can catch up. We were just starting. We are discussing about the format or how to write an IPv6 address and how to spot them when you get them in your configurations. So yes, as I was saying, this is an example of a complete IPv6 address. However, if you want something that is shorter, something that is easier for us to remember perhaps, and as you will see later on, when you write down your addresses, you will be using the first few blocks. Maybe out of a /32, you will be using the first /64, which is at the very start of your block, which has a lot of zeros. If that happens, then use these ways in which you can you can abbreviate or shorten your IPv6 address. How to do that? If you have a lot of zeros, if you have a lot of leading zeros, what I mean by leading zeros here is, if for each field, okay, for each of the field that is subdivided by your colon, for each of them, if there are zeros on the leftmost side, okay, and the most significant bits, then you can remove them. Okay, example, if you have 0023, they can easily use 23 and just eliminate 00. If you have 036E, you can eliminate 0 and just write it down as 36E. It means the same. You're not changing the values, you're just simply not writing down because it's obvious that you should have zeros there. However, if you look at these last two fields, 1250 and 2B00, they are not, okay, leading zeros. So when you write it down, it should still be 1250 and 2B00. Okay? Another way in which you can abbreviate your IPv6 address is when you have groups or sets of zeros. Okay? It should be adjacent fields of zeros. Okay? Example is this one. You have 3 fields. So far, what we've done there is abbreviated by removing the leading zeros, but still, you have 3 fields that are all zeros. So what you can do is just remove all of them. Okay? Once you remove them, you should replace them by double colons. So that's 2 colons successively, which is also called as a null value. Okay? So in this example, you know that this double colon represents 3 fields. Why? Because if you count them up, you will see 1, 2, 3, 4, 5. So you have 5 fields there, and you see a double colon. You know that there should be 8 fields in an IPv6 address. So you can rest assured that this double colon represents 3 fields of zeros. Okay, so that's pretty easy enough. However, one thing to note here is that you can only use the null value once in an IPv6 address. So only once. You cannot use it more than once. Why? Because it will be ambiguous. Let's just say for this example, you have, I'll write something on the chat here, okay? So you have 4EED 23 : 36E. Maybe you have another : Is this a valid IPv6 address? It's not, okay? You cannot have 2 double colons. Why? The first double colon might represent 3, the other double colon might represent 2, right? That's what we know because we know the full version. You can see the full value here. However, okay, if you notice, it can also be ambiguous. It can represent 2 zeros in the first null value and 3 zeros or 3 fields in the next null value. So nobody will know. So the idea there is never use a null value more than once in an address. Okay? Oops. Okay, next. Alright, so this is just an illustration just to show you how huge an IPv6 address is. Okay, things like Anil Gurung was gone. Okay, he's back now. Anyway, this is just an illustration of the entire IPv6 address and its representation in binary. Right, next. Here we have the IPv6 addressing structure. We can get a lot of things out of this diagram here. Okay, so if you haven't seen them before, I will explain it in detail. So, an IPv6 address has 128 bits, correct? So you have here from 0 all the way to 128. This is what we use to address, okay, or to provide an IPv6 address into a host. So each device will have a 128-bit IPv6 address. Okay, somewhere in the middle, we've divided our IPv6 address into two. We have a network prefix and an interface ID. You can think of this as the network and host bits in IPv4. So it's very similar in function. However, you should take note that an interface ID is always 64 bits. So it's always half of our IPv6 address. Okay, this value, the 64 bits, is assigned to the device itself or to the host, and it is assigned in many ways. It can be assigned manually, it can be assigned via DHCP, it can be assigned via random numbers, it can be assigned using values from your machine's MAC address. Okay, that is your interface ID, and that is always 64 bits. This is the reason why for end sites we can only assign, okay, the smallest network value, or the smallest block of IP address that you can assign for a single subnet, for a single network or VLAN, is a /64. So if in a network, maybe you have different VLANs, maybe one subnet for your finance team, one subnet for your technical team, another subnet for another, maybe another group in your company, then each of them will receive a /64. It doesn't matter whether you have 2 computers there, 4 computers, 1,000, 100, as long as they all belong to the same subnet, then you assign a /64 to that. Okay, next. Now let's focus more on this network prefix. So this part is, as I've said, considered as the network bits. So this is what you assign block per block on customers, on end sites, and also assigned from the RAR going to the ISP. So here you will notice that this part is like /32 bits. So when you request an IPv6 address, you request it from an ISP, from a registry, from a regional internet registry or a national internet registry. If you're a big ISP, you can possibly come directly to APNIC, okay, and request for your block. If you have an upstream provider, then you can also request your IPv6 blocks through them if they already have it, or come straight to APNIC to request for your block. Now, when you get your IP block, the normal maximum that you can get is a /32. Now, this is only for a single network. I mean, for a single company, organization. Now, this is already the size of the IPv4 address space, right? So this is a huge amount. However, if you think that this is not enough for your usage, you can always come back for more, request for more IPv6 addresses, or you can request for a bigger block when you do your requests. All right, when you submit your requests. Now, from there, from that /32 that you obtained, you will then delegate that to your customers. Your customers can either be an inside, it can be a university, it can be another smaller ISP, it can be a corporation, a big company, it can be government, it can be different things, right? So you have the option to give them a small block, as a medium-sized block, or a big block. Normally, what we give is from /64 to a /48. /64 for a very small one. If you have customers that are only using one subnet, maybe it's a home user where you don't expect them to grow in the future, then you can give them a /64. If you have something that is bigger, perhaps a medium size, a small office, home office type of setup, then you can give something bigger. but /48 may be too much for them. So maybe you can give them somewhere in between 64 and 48. That is /56. Notice that when I do give or delegate IP address blocks, I usually use nibbles. Okay, I use the nibble boundaries, meaning factors of 4. That's only because it's easier to do that way, and you don't have to worry about people or your humans or the administrators committing any mistake. So yeah, you assign /64, /56, /60, /48, and so on and so forth. Now, if you have big companies as your customers, you assign /48, especially if it's a multinational or a multi-homing type of organization. So if you are an ISP, you got your /32. Essentially, if all your customers are big customers where you will give /48 to each of them, then that means that you can have a total of 2 raised to 16 customers, each of them with a /64. Now, if this is not enough, you can always again come back to APNIC, come back to your RIR, and request for any subsequent allocation. All right. So essentially, from this slide, what I want you to get is the structure that you can get from IPv6 addresses. You can only give as much as this one. Okay, if you're subdividing or doing your subnetting, the smallest block that you can assign is a /64. Again, that is because of the limitation that we have with this interface ID. Most operating systems, if you assign an IP address to them, they don't even ask for subnets or for the slash notation. It is assumed by default that it is a /64. So again, that's a limitation that we have here. All right. So any questions about this structure? If not, I'm going to go to the next slide. So this is just an illustration of how IPv6 addresses are delegated from the RIR, going to the members, going to end users. So as I've said, normally you get a /32, which is what you can see here. You'll notice some wordings there like allocation and assignment. Allocation is just when it is provided to yourself so that you can further delegate or assign that to your customers. Whereas if it's assignment, once it is given to you, you will use that to assign to your own network, assign to your own infrastructure. So that's the difference between assignment and allocation there. There's also portability and non-portability. When you say portable, when you get that request, when you've requested that IP address block from APNIC or from any RIR, then that is a portable address. If that is taken from, let's say, your upstream providers, then that is a non-portable address. So you can see here, this is from APNIC, that's portable. This is from APNIC, that is portable. This is from the member, from this member going down, that is a non-portable. This is non-portable. This is also non-portable. But more importantly, what you should see here is the amount of blocks that you provide. There is no such rule like what is the size that you can delegate to your customers. Okay, the only rule that you can find so far in the policy document is that all /48 assignments that you do should be properly added in the WHOIS database so that there is a record of all these assignments. But otherwise, it's easy. You can have your own policy. It will depend on your company's policy, what size you're going to give to your customers, right? So here you got a /32. He has a smaller ISP, which is his customer. Okay, so he gave us /40. Now this customer, which is also an ISP, assigned /64 blocks to its customers, whereas this bigger member assigns /48 to its customers. All right, so that is how you delegate IPv6 addresses downstream. Any questions? I can see someone typing down, so I'll wait for you to finish that before looking back into the chat. But right now, if it's okay, we will continue and we will discuss the IPv6 addressing models. Now, IPv6 addressing models just tells us or discusses the different ways in which we send and receive packets all throughout in the IPv6 data packet stream. So it can be unicast, anycast, and multicast. as you can see, there's no broadcast. So this is the same addressing models that you have in IPv4, except that there is no broadcast. Okay, so let me just finish this before getting to Anil's question there. So unicast is when you send packet from a single interface going to another single interface. So there's a one-to-one relationship between the two devices here. One source interface, the destination address is also pertaining to a single interface. When you say anycast and multicast, that's one-to-many, a single source interface, many devices on the receiving end, so one is to many. So your source your source address is a single interface. However, your destination address pertains to or is assigned to a group, okay, a group of many machines that are sharing that IPv6 address. So with anycast, you have an anycast group here, but only one among everyone in that group will be able to receive the packet. Only the one that is nearest. Can be this machine, can be this other machine. All of that depends on whether, okay, you based on the metrics that your routing protocol is using, your machine or your destination is the nearest to the machine sending the data. Okay, and multicast again is very similar to anycast, as I've said. So with multicast, essentially when you send a message, when you send a data, okay, it will be received by everyone that is part of that multicast group. So everybody receives it. I only have to send out one set of messages and everybody will have it. I don't have to send them separately. That is multicast. Now the reason I want to show you this is so that you can, at the back of your mind, when we discuss the different types of addresses, when you look at the different addresses, you can categorize them, whether it is unicast, anycast, and multicast, and you know their function. You know or you understand that for this particular address, it will be sent to many, okay, many machines, not just intended for a single machine. All right, so just try to remember this for now. Okay, so if there are no questions for this slide, I'm gonna go and read Anil Gurung's question, which is, does the IP provided by portable to non-portable is reachable via the internet? Okay, let's get back here. All of the blocks that you get from the RIR are considered part of, if you want to use IPv4 terminologies, we call it the public addresses, right? In IPv4, we have public and private addresses. We have such things in IPv6 as well. The ones that you request from the RIR are public, meaning they are reachable via the internet. Okay, so the only difference here is portability and non-portability is that if it's portable address, since you request that from APNIC, from the RIR, it means that you can use that even if you change your upstream providers. Again, because this is portable address, you did not get this block from your upstream provider. However, when you say non-portable, you got that from your upstream provider, which only makes sense that when you stop using their services, you have to return it back. And when you return it back, you have to get another set of IP addresses or IP address block from your new upstream provider. Okay, so that's the difference. But if it's reachable or not, yes, all of them should be reachable because they are part of what we call as the global address or the public addresses. All right, so I hope that answers your question, Anil. Now, moving forward, let's go and have a look at the different types of addresses. So before we do that, so one thing that I want you to remember here, when you enable IPv6 on an interface, maybe you open your machines now, you're on your Windows or Linux or Mac OS X computers at the moment, and you enable IPv6, again, for some cases, it's already enabled by default, you should see an IPv6 address next to your interface, next to your interface card. So, what type of addresses are there and what are they for? What are their coverage, so to speak? So we will look at that. So we will be able to identify that. Now, we have, like in IPv4, we have a similar structure. So we have loopback addresses, we have unspecified address, and so on and so forth. Loopback addresses in IPv4 is simple. It's 127.0.0.1, right? In IPv6, it's even simpler. We have : 1, okay? : 1 because it's just 1 and everything else is 0. And as you know, all the 0 fields can be represented, can be shrunk down and represented as a double colon. That's why we have a : 1 here. Okay, now it has a /128. So that's again similar to the network prefix in IPv4. In v4 we have a /32 if it pertains to a single address. Now in IPv6, since we use 128 bits for address bits, then you use /128 to refer to a single interface, to a single IP address. So our loopback address, as I've said, is : 1 /128. Now, it's normal that we don't put the /128 there because it's obvious that it refers to a single address. But in other cases, you have to specify the network prefix. Okay, it always comes in pair. Your address plus the network prefix. All right. An unspecified address in IPv4 is 0.0.0.0, right? In IPv6, again, it's the same. It's all zeros. So in our case, again, going back to the methods of abbreviation, you can just represent that as a double colon. So double colon /128 is your unspecified address. We have two others, which are both /96, which was used in the early days of the internet, of IPv6, more specifically when we are transitioning from v4 to v6. Now this is a good way for developers, for those that are creating firmware, okay, low-level programming, because they don't have to recreate the programs whenever, okay, there is a shift between, let's say, using the IPv4 transport or the IPv6 transport. So if you're using IPv4, you basically will just grab the first 96 bits and the last bits, 96 to 128, which is 32, okay, that represents the IPv4 address. So if you need the IPv4 address only, then you'll grab the last 32 bits of the address. Otherwise, you grab the entire thing, okay, to represent the IPv6 address, okay? So that is what IPv4 mapped address and IPv4 compatible address is about. Now, IPv4 mapped address is already deprecated, okay, it is no longer used, but IPv4 compatible address is still being used. Why /96? Again, we are referring here to a single IP address, similar to loopback and an unspecified address. But we are referring to two addresses. One is the IPv6 address, which is what we get if we use the entire, okay, the entire 128 bits, and the IPv4 address if we're using only the last 32 bits. So normally, you see it written down as like this: FFFF : 192.168.1.20, something like that. Because the last 32 bits, so 128 minus 96 equals 32. So the last 32 bits, that 192.168.1.20, represents 32 bits. Okay, so it's just an easier way so that you have compatibility between v4 and v6. It has nothing to do with the /64. Okay, again, we're referring only to a single IP address, and that's 96 because that's 128 minus 32. All right, so I hope that answers your question. So I hope this is clear: IPv4 mapped and IPv4 compatible address. Now, there are others, of course. We have a lot more different IPv6 address ranges which are used for different purposes. We have an unspecified and loopback address, which we've already discussed. We have global unicast address, which is equivalent to the public address in IPv4. So the block there, okay, is 2000:/3. So if you already have your IPv6 address, check whether it falls in this block. Obviously, it should be, okay? That's because that's our publicly available IPv6 block. We also have link local address, multicast address, and unique local address. Each of them are represented, okay, uniquely by the first number of bits. In link local's case, that's FE80. So the first 10 bits of your IPv6 address, okay, identifies this group. So F, that's all ones. This is E, this is 1 0, and then you add 2 zeros to complete the nibble. That's 8, and then FE80 because you want the whole field. So FE80, once you see that, you should know that it refers to a link local address. This is the most common address that you will find. If you have IPv6 enabled on your machines right now, you should see an IPv6 address that starts with FE80. Right? Next one, you have multicast address. Now, if you're not sure what this is used for, we will look at, I think I should have some slides here that shows us how to do the neighbor discovery process. So it uses multicast, and we use this block FF00/8 for all multicast type of addresses. And you also have unique local address, which is FC00/7. So again, this block is defined by the first 7 bits. So you'll have to look at the network prefix. Okay, so the bits in the prefix tells us the number of bits in the network fields that defines that address range. So in unique local address, that's FC00/7, which is the first 7 bits. Alright, so let's try and discuss each of them more clearly. Let's start with link local address. Link local address starts with FE80. We've already discussed that in the previous slide. But what is the use of a link local address? Now, as I've said, this is the very first address that you will find or you will discover or see once you enable IPv6 in your machines. This is a special address. It's a mandatory address. It is necessary. You will definitely have a link local address. And it is only allowed, it is only visible in the local link. So in one subnet, in one network, all the machines that has a link local address should be able to see each other. So you see how important this is. Even in routers, it is used. Even in routing protocols, as I said, it is used. Now, you don't really need to do anything. Once you've enabled your v6 in your machines, you will get a link local address, and you can already use that. That's a valid IP address that you can use, again, only in the local link. It cannot pass through a router. So if you have 2 networks separated by a router in network A cannot see the machine in network B if they're separated by a router or any L3 or L2 devices in between. Next is the unique local IPv6 unicast address, or simply that's unique local address, because we all know it's IPv6, we all know it's a unicast address, right? So ULA is the acronym for unique local address. This is, you can think of this as similar to the private addresses in IPv4. So private addresses in v4 include 192/8, 172.16/12, and also 192/16 and 192/10/8. So all of those are IPv4 private addresses. We use it to assign in our local networks, but those IP addresses are not visible. It's not available on the global routing table. It's not reachable via the internet. Again, only available locally. So in IPv6 world, we have a similar function with ULA. It's used only within your network. However, one thing that is different with this is that it is unique all over the internet. So there's an algorithm that can be used to generate ULA addresses, and there is very little probability that any 2 addresses will be the same for if you assign them to 2 different networks, that both of them will have the same value. So it is unique worldwide. However, you only use it locally. Okay? Now, unique local address, before we had this, there was site local address, or SLA. So that is, you can think of it as the one that preceded ULA, but that one is already deprecated. The reason for that is the problem with ambiguity, the problem with uniqueness. Okay, with site local address, you can assign similar IP addresses into one site. Okay, your address is only valid, it's only unique within one site. But it is vague whether a site is just consists of maybe a small network, small subnet. Maybe it pertains your whole ISP network. Maybe it pertains a one network. So there is an overlap with the different sites. So you cannot be assured that you have a unique address, and that can be an issue. So again, ULA is the SLA is the predecessor of ULA. So we're using ULA now, which is unique everywhere in the world. Now FC00 is the block we use for ULA. Now if you look at some generated values from these links, it's actually at FD00, right? Or FD, basically the other half of the block. So this /7 can be divided into two. One /8, another /8. So the ones that we see generated are coming from the second half of this block. Alright, so I've mentioned about the global addresses earlier, which is the public addresses, if we use the IPv4 parlance here. So that is 200/3, which is essentially from 2000/3 all the way to 3FFF. Okay, so you write all F's there until you reach hex number 32. That's already a /3. Each of the 5 RARs got their /12s from that /3 block. Okay, so basically IANA, or the Internet Assigned Numbers Authority, they were the ones who were giving out, they have the entire IPv4 and IPv6 pool. When it comes to IPv6, they distribute /12s to each of the RARs. Okay, so all the 5 RARs now have their own /12s, and they still have about 506 in their pool. Okay, so when you request your IPv6 block from APNIC, it should be within this range, 2400/12. Okay, so this is the public address. This is the global address. This is the ones that you see announced, originated on the routing table. These are the ones that you assign on your publicly facing networking equipment, networking devices, such as your routers and your servers. And it should be reachable from anywhere on the IPv6 internet. Okay? The next one is a 624 address, which starts with 2002. You'll see this assigned when you're using tunneling. So if you are using tunneling mechanisms, you're using tunneling services from a provider, then they should assign a 2002 block to you. Okay? But you can also use this otherwise if you're just setting up, let's say, a private tunnel. But basically, this is for 624 types of tunneling mechanisms. We have other blocks too. In IPv4, we have a range that is used for documentation purposes. In IPv6, we have the same. Now, this is used, of course, if you're creating journals, you're creating examples, creating books, where you don't exactly want to use publicly available addresses, because if someone used them, if someone used your example in an experimental setup perhaps, or in a, let's say, yeah, in test setup, a lab setup, then if they use publicly available addresses, it might cause some chaos. So we don't want that. So you either use the example values, which is 3FFF/32, or more commonly, I can see this documentation block, which is 2001DB8/32. Again, for everything that has to do with writing down documentations, examples, how-to documents, then you use this block, not your actual IPv6 address block. All right. So those are the different network prefixes in their different uses. One thing that I want you to remember here is that when you have an IP, you have, let's say, an interface that has IPv6 enabled, you will definitely have a link local address. That's mandatory, right? After that, you have the option to assign a unique local address. Maybe you're assigning ULA to all the machines in your network. That's okay. So you can have a linked local address, you can have a unique local address. If you want that machine to be visible on the IPv6 internet, you can also assign a global address. So this is optional, ULA is also optional, but all of these can be assigned to a single interface. Okay, so that's the difference. In IPv4, you need two interfaces to assign. Let's say maybe your machine will be visible locally and also publicly. So you have two different interfaces which has different addresses. With this one, you can assign many network prefixes to the same network interface. Alright, so I hope that's clear enough with everybody. Okay, I've mentioned about the interface ID. That is the first another half of your IPv6 address block. Okay, we've discussed about the network prefix part. So here, this is the lowest 64 bits of your address. Again, it's fixed 64 bits, and it is assigned in many ways. It can be assigned using DHCP, like an IPv4. You can be assigned via DHCP v6. It can be assigned via manual configuration like this. Okay, it can be assigned by using EUI64 and also pseudo random numbers. I think I have that here. So yeah, for EUI64, you'll notice it says here that it's based on the MAC address of your machine. So your MAC address is a physical address. It is unique on your machine. Each device has its own physical address based on the manufacturer again, okay, and some unique values as well. So based on that, that's 48 bits, you can come up with a 64-bit value. So how do you do that? You subdivide your MAC address into two here. So the upper bits and the lower bits, you add FFFE there, okay, and you look at the 7th bit. So the 7th bit is somewhere here, which is this one, and you toggle that bit depending on whether it's this value or this address is unique or not. So you toggle it from 0 to 1. So with that, you have come with this value. So 0226B0. Again, this part is based on the MAC address, the first upper bits here, except for the 7th bit. You add FFFE, and then you copy the lower bits. That's it. That's it. That's your 64-bit modified EUI64 value that will be assigned to your machine. So right now, if you look at your interfaces, if you have IPv6 enabled there, you will most likely see, okay, an IPv6 address that has an EUI64, okay, interface ID. If you're using Linux, if you're using older versions of Windows, EUI64 is the default values. However, if you're using, okay, latest versions of Windows and also Mac OS X, it uses random numbers. So see this one? Auto-generated pseudo-random numbers. Your operating system will just essentially create or assign random values to the 64-bit interface ID because they don't want to use EUI64. So what is the implication of using this? We are using the machine's MAC address. And MAC address is, again, unique to your machine. So whether I'm here, whether I'm in the US, whether I'm traveling somewhere in Asia, my interface ID will remain the same. And security practitioners would say that it can be an issue. It can be a security issue, okay, if you use that. So that's why there is another option to use random numbers. All right. Now, another thing that you would notice if you're using Windows, and even if you're using other operating system, there is what we call a zone ID. And this is because we are using, okay, the same interface for different addresses. So how do you know which address or which network, which subnet use or send that packet, or which one should receive that packet? So we use zone IDs to identify those different zones for the different addresses that are assigned on the same physical interface. All right. So in Windows, you can see it as a percentage. So %4, %3. It can be any number that is assigned by your machine. In In Mac OS X, I think it's not using percentage, it's using another symbol, but you should also see something very similar. All right, but just notice something that you need to remember here is that, let's say, when you're sending packets from host A to host B, you are using your own zone ID and not the other machine's zone ID. And that's because zone IDs are only valid, okay, they are only identified locally. The other machine does not have an ID of your own zone ID. So if host A here has zone ID %4, host B has %3, if I want to ping host A to host B, I will ping host B's IP address, which is this 3001. So you can see that here, 3001. However, notice that I used my zone ID, host A's zone ID, which is %4 and not %3. Okay, so if you are trying to troubleshoot, perhaps you're trying to do a ping and for some reason it just always times out, try and use it with a zone ID. Okay, see if there is a difference. All right, so any questions? We're just about winding down, but we still have a lot of things to cover here. Here is auto configuration. So I've mentioned that when you're using link local address, you will automatically receive an address, right? That is part of auto configuration. You will get, whether you're using stateless or stateful, you can have the option to get your IP address automatically. Okay, and you use that for machines that don't necessarily need to have static addresses. So for those that are not used as servers or routers or network equipment where it should have a specific address all the time, then you can use stateless mechanism, and that is assigned automatically. This is how you do auto configuration, or basically how you assign an address to a machine. So let's just say you have this machine, this new host that's just been turned on. It needs to have an IPv6 address, right? So the machine itself, based on its MAC address, based on, of course, the link local address range, it can have a tentative address. Now, it's not assigning the address to the interface yet because he needs to check. Even if, let's say, with this one, you have 98% assurance that it will be unique because, again, it's based on your own physical address. But you still have to check, right? So he's going to check whether someone else in the network is already using that. So he's going to send a query. It's called the Duplicate Address Detection, or DAD. It's part of the neighbor discovery process. And this particular process is what we call as a neighbor solicitation. So he will send a message to everyone. This is not broadcast. Remember that. There's no broadcast in IPv6. It is sent to a multicast address. And remember, our multicast address range is FF00, right? So the multicast address range for solicited node addresses is FF02, which is part of your multicast range. So it will send that address to here, and everybody in the network who are listening, all the machines and hosts here, should be listening. Now, if there is no one using the same address, then there will be no neighbor advertisement. Okay, if there's none, then I can now assign that address. So I now have a link local address assigned to my interface. Now the next one is, I'll try to find out whether there is a router that's advertising either a unique local address range or a global range. So I'll find a router. It's what we call as a router solicitation. I'll send out to another multicast group, which is FF02::2 for all routers. If you have a router, it should be listening to that address. So I'll send that one. I'll wait for a router advertisement. Now the router advertisement is a bit different than a DHCP reply, right? Because it only contains a prefix, the network's prefix that is assigned to this link. So you will only receive a /64 or /48 or things like that. Okay, once I receive that, I will use that as a network part of my address, and the rest I will be using my interface ID, which is either using my EY64 or any random number. So that's how I will assign a global address to my interface. So by the end of this process, you have a link local address. If you have a router in there, it's announcing something, you can now get a global address as well. So that's how auto configuration works. Again, it's very similar to how in IPv4 you try and find out the addresses, right, using broadcast. You do ARP to find out the physical address of the machines. It's something very similar to that, but since we don't have broadcast in v6, we are using different multicast addresses to do something as a function that is similar to that. Okay, so that is the end of IPv6 auto configuration. Questions? No questions? So next is subnetting. We don't have enough time, but I will just quickly go through the subnetting example, and then I'll leave you to do the exercises, right? Subnetting in IPv6 is not very different than subnetting in IPv4. It's exactly the same, although you have to be careful because again we're dealing with hexadecimal digits here. It's very easy to get confused whether we're seeing a 0 in hex and a 0 in binary. So you have to be careful, but otherwise subnetting, the process itself should be similar. So here we have an example. We have a /32 and we want to delegate blocks to our customers. We'll be giving /48s to our customers and we're asking for the first 4. So what do? The easier way to do it, which is what I tend to do when I was starting out with this, I rewrite them as the block that I'm asking. So since here we are asking /48, so I rewrite them as a /48. So /32 /48 is just an extra field. So you add 4 hexadecimal values there, 4 zeros, and then this extended there. That will be your network prefix. Okay, that's a number of /48 blocks in a /32. But what I wanted to look at is the values for the first 4 /48. So I know that I should be working, my block is /32. You have a demarcation line there. This is the block that you're trying to find out. So you have this number, this range to work on the bits. And similar to IPv4, you just increment the bits. But this, notice, is hex. So write them down in binary. So that will be 16 binary digits. Okay, you start with 0, increment that 1, 1, 0, 1, 1. Alright? But that's not the end of it, because you have to move that back into hexadecimal digits. Write it back into hex, because this is in binary. So you write it down in hex. So this first one is 0, 0, 0, 0. Okay, the next one is 0, 0, 0, 1, right? The next one is 0, 0, 0, 2. And the last one is 0, 0, 0, 3. Okay, so that's a difference. I see some people just write down 2001 db 8000 1011. That's not correct. It should be these values 1, 2, and 3, because you have to write it back into hex digits. So that's your value. Again, it's very simple. You just require some practice. So now I have some exercises here. If you can try and do this. If you're not sure whether you got the answers correctly, please send me an email so I can verify if you got it correctly or not. I have just 2 exercises there. Try and do it at home and then send me an email to verify your answer. Alright? So that is it. If there are any questions, I can take them now. Otherwise, I'm also gonna write the link on the chat so you can fill in the survey. Any questions? Now, if you're looking for the slides, it will be available after you've finished the survey. So you will be redirected automatically to a page, to an FTP site, where you can download a PDF copy of all the slides for today. I'm trying to wait whether there is any question on the chat. There are people typing, but I'm not sure if it's a question or a vote of thanks. But anyway, if you don't have an IPv6 address yet, please contact our help desk. And if you have an IPv6 address and you're looking at transitioning to v6 from v4, then look at our website. We have an IPv6 APNIC page there that lists down some of the industrial experiences, some of the presentations done by major providers that have done this in the past. So have a look at that too. Alright, if there are no questions, thank you very much everyone. I appreciate you coming for this class. Again, any questions, please feel free to send us your questions. Alright, thank you again, and if it's still morning in your time zone, have a good day, and I hope to see you again in another e-learning session.